Alright, let's start off this video with the challenge problem from the last video. So we have a block attached to a secure spring oscillating on a horizontal surface, and we're given its maximum speed to be v, and now we want an equation for the spring constant, or sometimes you'll hear it referred to as the force constant. And by an ideal system, this just means that there's no friction, no external forces that are going to do work on the system, so we can just use our regular conservation of energy equation. That's just all that means. So as I told you in the last video, a little hint is that our maximum kinetic energy is going to equal our maximum elastic potential energy, and that is because we know that Ke plus Ue are the only two types of energy we have, so they're always going to add to the same constant at all points. Now at the minimum and the maximum where the spring was released, it was released from rest, so at the minimum and maximum points kinetic energy is 0, so we just have our elastic potential energy that equals our constant. However, when the spring is passing through its equilibrium, it's not stretched at all, and our elastic potential energy is 0, so our kinetic energy equals a constant. Those 2 points are where those two energies are at their maximums and they equal the same constant. Therefore, our maximum kinetic energy equals our maximum elastic potential energy. Now we know our equation for kinetic energy is 1/2 mv squared. We know our equation for elastic potential energy is 1/2 kx squared. We can multiply both sides of the equation by 2. And now it's just some simple algebra to see that k is going to equal mv squared over x squared. And there's your equation for the force constant. This problem is a lot like the last one, except this time we are solving for the maximum speed of the mass as it passes through equilibrium. Alright, well, let's start by writing our conservation of energy equation and set our zero line for gravitational potential energy to be through the center of mass of the block. So then our kinetic energy plus our elastic potential energy will equal some constant. Now when the mass is passing through equilibrium, x, its displacement from equilibrium, is 0. So we'll have no elastic potential energy, and kinetic energy will be at the maximum as the mass passes through equilibrium. Alright, and now as you might be able to tell from the options, we also have variables like x and k that are present in our elastic potential energy equation. And that's because Ke max, the speed of the mass as it passes through equilibrium, is equal to its maximum elastic potential energy. So in that case, 1/2 mv squared, where v is maximum velocity, equals 1/2 kx squared. We can multiply both sides of the equation by 2 and algebraically solve for v to get kx squared divided by m. Take the square root. The square root of x squared is x. We can do that because everything is being multiplied or divided. So we see that v equals x square root of k over m, and that would be option A. So hopefully you're getting a little bit more comfortable with manipulating our conservation of energy statements, and now we're working on algebraically solving for different variables. Alright, this problem is a little bit trickier. We're looking for the change in potential energy of a pendulum bob pulled back to an angle theta. So we're going to set its length when it's just dangling from the horizontal to be our zero potential energy. Now our change in potential energy is going to be mg times the change in height of that pendulum. Alright, so this is going to be the length of the pendulum bob when it's just dangling vertically. And this is its new length at an angle theta. This will be a right triangle, and this will be L. And we want that distance, I'm just going to call that X, because that's its height. So the bob was here at 0, and now it's a distance X that's contributing to its potential energy. So first let's solve for this length. We know cosine of theta is going to be our question mark over our L adjacent over hypotenuse. So this height here, our question mark, is L cosine of theta. So that means our X is going to be L minus that question mark. So it's going to be L minus our L cosine theta. So we can factor that to be L times 1 minus cosine theta. So our change in height, we already have mg, those are given. Our change in height is going to be our final height minus our initial height. You know our initial height is 0, and we just solved to our final height. It's that x value. Right here, we know that is L times 1 minus cosine theta. So our answer is going to be mgl times 1 minus cosine theta, which is our option A. Here is the last problem for this video. So we have a rock of mass m thrown horizontally from a cliff of height h with an initial speed v. We want to know its kinetic energy just before it strikes the ground. Alright, so first let's decide what types of energy do we have. Well, the rock is moving, so we have kinetic, and there is a height h involved, so there's potential. And for convenience, let's set this to be 0 gravitational potential energy. Alright, so we know that our energy initial equals our energy final. We know our initial energy involves kinetic, and the rock is above our 0 line, so we have potential. And our final energy, we are solving for kinetic. So when the rock strikes the ground, or just before it strikes the ground, we're saying that little bit of height above that 0 line is practically negligible, so the only final energy we have is kinetic. So this right here is actually what we are solving for. So now we just need to put in our equations. So we know kinetic energy is 1/2 mv squared. We are given those variables. We know our potential energy is mgh, and we are also given those same variables. And that is equal to our final kinetic energy. And that makes option C the correct answer. They're just switched. So if we were given h to be something like d or x, we would have had to substitute that instead of h. But because we're given all those same variables, we can just put in those equations. Alright, here's the challenge problem for this video. The solution will be on my Instagram page about 24 hours after the release of this video. You can find the link in the description, or you can find the video solution at the beginning of the next video, which will be on work.